Hello everyone. Today we will continue our discussion on calculation of resistance and conductance, and today we will do calculation of resistance in the case of diffusive transport. And if we have a quick review of what we have done so far, this is what we started our discussion with. We started with these expressions. These are conventional expressions for conductivity and resistance for 1D, 2D and 3D conductors. These essentially comes from the conventional theory of transport, which has roots in Root's model of transport. And in last class we or in last few classes, the emphasis has been on the point that the starting point should be this, or the starting point for these kind of discussions should be this expression, the expression for the conductance from the ballistic transport case. Okay. So, so we should start the discussion with this expression 2q square by h Te me minus del f by del E dE. And from here, in our last couple of classes, last class particularly, we calculated the conductance in the case of ballistic transport to be this. And as you can see, this has this constant term which is known as the quantum of conductance multiplied by the number of modes in the conductor at Fermi level. So, this was the case when T was 0 Kelvin in a ballistic conductor, and when we operate at higher temperature, at room temperature maybe, in that case we need to do exact calculation of this integral as well as this differential in this as well as this derivative in this equation. And so this becomes first we need to do integration and then we need to take differentiation, and it becomes quite a complex expression because we need to integrate this expression, and number of modes is also in some cases it is not a straightforward function. So, this is tackled by what is known as Fermi Dirac integrals. So, that is what we also saw in our previous classes. So, we have seen calculation for ballistic transport case with the help of Fermi Dirac integrals. Today we will see how things happen in the case, or what are the conductance and resistance in the case of diffusive transport. And that will essentially conclude our discussion of the transport theory. We will briefly have a look at the practical 1D, 2D conductors, because we are assuming till now we are assuming that these 1D and 2D conductors are ideal 1D, 2D conductors, but actually they are not, because a 2D conductor has a finite thickness, this thickness T, which leads to quantum confinement in this direction, and a 1D conductor has confinement in two directions, the directions apart from the long dimension. In two other dimensions there will be electron confinement, and that will introduce some that we also need to take into account while doing the final calculation for practical conductors. Okay. So, that is what we will see, and this was the expression for conductance for a 2D conductor in ballistic case. When we have a 2D ballistic conductor, this is the final expression, and we studied some properties of the Fermi Dirac integrals. With those, with the help of those properties, we can actually calculate this value. Okay. So, so today let us see how this looks like in the case of diffusive transport. So, generally in diffusive transport case, generally we assume that a conductor is a bulk conductor, purely diffusive transport. In that case, this transmission coefficient is equal to lambda E by L, Te is equal to lambda E by L. But in intermediate cases, when the conductor has electron scattering, but the conductor is not extremely long, it is not a bulk conductor, it is in the intermediate length scale. In that case, the transmission coefficient needs to be taken to be Te is equal to lambda E divided by lambda E plus L. So, this is the pure diffusive limit. Te is equal to lambda E by L is the pure diffusive case. And this is actually a more general case. So, this will hold true even in the case of ballistic transport and also in the case of diffusive transport. So, again we take the channel to be a 2D channel because of the sake of simplicity to visualize transport, and also there is some simplicity in calculations as well, and the starting point like always for us is this expression. So, the conductance is 2q square by h integral of Te me minus del f by del E dE. So, in the case of pure diffusive transport, in that case this Te is equal to lambda E by L, and generally this number of modes can be written as W times number of modes per unit width m2 dE. So, that is how we can generally write the number of modes. Okay. So, if we put that these two expressions in this, the conductance turns out to be 2q square by h lambda E me minus and this me can be replaced by W times m2 dE. So, we will write it to be in terms of m2 dE, and W from here can be taken outside, and similarly L can also be taken outside. L by lambda L from the Te can be taken outside. And now as you can see that now the conductance is inversely proportional to the length of the conductor, directly proportional to the width of the conductor, which is actually true in the case of conventional expressions of conductance and resistance as is written here. So, for a 2D conductor, the conductance should be, according to the conventional theory of transport, it should be inversely proportional to the length. So, that is true in the case of purely diffusive transport in the conductors. Now, the conductance has become inversely proportional to the length. But as we have seen earlier, in ballistic case, the conductance or the resistance is independent of the length. So, we cannot use our conventional theory of electron transport in ballistic case, or even in diffusive case or in intermediate cases when we have some scattering, but the conductor is also not extremely long. It is not a pure bulk conductor, it is in the intermediate length scale. In that case also we need to actually start the treatment of electron transport from the basics like here. Okay. So, so if we further simplify this expression, this will be actually we need to find out this number of this scattering of electron. This lambda essentially comes from the scattering in the channel, and this is the topic that we have not dealt in detail. This topic is not dealt with in detail, the scattering and how the scattering length, the mean free path of the electrons, can be calculated as a function of energy. So, we will see if there is time left, we will also revisit the scattering and try to calculate lambda in terms of as a function of E. But at the moment let us assume that we are aware of this, we are aware of the mean free path or the scattering mechanisms in the channel, and From there, if we put the expression of lambda E in this conductance expression, we can calculate the conductance in the diffusive case. Okay. So we again, like a ballistic conductor, we will see how it looks like when T is equal to 0 Kelvin at extremely low temperatures, because the calculation is much simpler in those cases, and how it looks like at practical operating temperatures, the room temperature or even higher temperatures. Okay. So let us first see what happens at T equal to 0 Kelvin, and like we know, this Fermi window function minus del f by del E function, this boils down to a delta function at Fermi level at T equal to 0 Kelvin. So at T equal to 0 Kelvin, this becomes a delta function, and this greatly simplifies the expression or this integrations. So now a 2D diffusive conductor, the conductance can be written as 2q square by h integral of lambda E m 2d E minus del f by del E can be written as delta E minus EF dE, and all this times W by L. Okay. So if we have a delta function in the integral, this essentially simplifies the integral like this. Now this lambda EF m 2d EF will be there. So this is essentially the diffusive conductance of a conductance in the case of diffusive transport, when the transport is purely diffusive. Okay. So and if we try to write it down in terms of ballistic transport, the ballistic conductance is given as 2q square by h at 0 Kelvin m 2d EF. This is the ballistic conductance. So this diffusive conductance for a 2D conductor can be written in terms of ballistic conductance as lambda EF by L times G 2D ballistic. So what is the only difference is of this term. Now we need to in case of diffusive conductor, we need to know the scattering at Fermi level, scattering length of electrons at the Fermi level when we are trying to calculate the conductance or resistance at 0 Kelvin. And lambda this TE needs to be replaced by lambda by L. And in a more general case, when we are treating or when we are considering both ballistic and diffusive conductors, we need to replace TE by lambda E divided by lambda E plus L, and in that case this expression will simplify to, instead of this expression, what we will have is G2D diffusion will be 2q square by h integral of lambda E divided by lambda E plus L m 2d E minus del f by del E dE times W. So that is what we will be having in this case, W. Okay. And at T equal to 0 Kelvin, this will essentially be the conductance of a diffusive conductor or any conductor. In a more general case, let me write instead of writing a diffusive here, in a more general case, the conductance at 0 Kelvin is 2q square by h lambda EF divided by lambda EF plus L times MEF, where MEF is W times M2D EF. So, this will cover both ballistic and diffusive cases. Okay. So, as always, the calculations at T equal to 0 Kelvin are not difficult, and this is how it would look like. So, we can also write it down as G2D is lambda EF divided by lambda EF plus L times G2D ballistic conductance, or the resistance, which is essentially the inverse of the conductance, is L plus lambda EF divided by lambda EF. 1 by G2D ballistic will be the ballistic resistance. So, this will be essentially 1 plus L by lambda EF into ballistic resistance. That is the case when we have T equal to 0 Kelvin, and as you can see that this resistance, ballistic resistance, is independent of length, but the diffusive resistance is not independent of the length, and we as we go deep into diffusive limit, as we make the conductor large enough, in that case this term dominates and resistance is directly proportional to the, becomes directly proportional to the length of the conductor, as is the case in conventional transport theory that we sort of with which we began our discussion. Okay. So, this was a low temperature case, extremely low temperature case actually, and as we saw in the case of ballistic transport, things are a bit difficult when we have high temperature or normal temperature, because the maths is difficult in that case, because in that case this in this expression of conductance, this minus del F by del E function, this cannot be replaced by the delta function, and we need to explicitly do this calculation in order to calculate the conductance. And but as we have seen that with some mathematical tricks we can manage these calculations as well, particularly in the case of non-degenerate semiconductors, because in the case of non-degenerate semiconductors most of the electrons are close to the bottom of the conduction band. So, if we have the valence band, the conduction band, most of the conduction electrons are quite close to the bottom of the conduction band, and in this case even the Fermi-Dirac function can be approximated by the exponential function. Things are more difficult when we have to deal with degenerate semiconductors or extremely highly doped semiconductors. Okay. So, so we at T greater than 0 Kelvin temperatures, at room temperature also, we begin with this expression, and now we sort of make this replacement. Let us say that we write it down, we write this term M2DE minus del F by del E. This we can write down as the average of M2D over all energy values, and the reason we can do that is because this integral is minus del F by the area under Fermi window is 1. So, this can be written as m, so this can be written as m2d E minus del F by del E dE divided by minus del F by del E dE, because this denominator is anyway 0 anyway 1. So, we can always put this term in denominator, and this is essentially the average of the function m2d E. This average is taken over all energies in the Fermi window, and what it essentially means is, as we have also discussed at some point earlier, that this means that this is the number of modes averaged in the Fermi window. Okay. So, so now what we do is we divide and multiply this term by this average. So, G2D diffusion conductance is 2q square by h lambda E m2d E minus del F by del E dE. We multiply and divide by this average function, and in the denominator we write the expanded version of this average, which is m2d E minus del F by del E dE, and of course we have W by L as well from here. Okay. So, now this is the conductance at normal temperatures. If we have a closer look at this expression is also like an average of a function, average of essentially this function lambda E, and now this average is taken over this function m2dE minus del F by del E dE. So, what it intuitively mean is that we can write it down as G2D diffusion conductance at normal temperatures to be 2q square by h average. We have used a different sign for this average just to make a distinction between the average of m2dE and lambda E, because these two averages are of different kind. This average is taken over the Fermi window, and this average is taken over the modes in the Fermi window times W by L. So, now what we can essentially intuitively say is that the conductance is obviously is given by the quantum of conductance multiplied by the average or average number of modes in the Fermi window times the average mean free path of electrons in the modes in the Fermi window. So, this function intuitively means this is the average mean free path of electrons in the modes in the Fermi window. So, from this expression we can intuitively say that this is the average mean free path of electrons in the modes where conduction happens, and the modes where conduction happens is the modes in the Fermi window times W by L. So, as is evident here, conductance is inversely proportional to the length, directly proportional to the width, as we expect in the case of a diffusive conductor. Okay. So, so this is the core sort of result here, and these calculations, if we know the exact expression for lambda E, we can do these calculations, and this can be calculated with the help of the Fermi-Dirac integrals. Okay. So, so this is essentially how it looks like. We will not do the exact calculations because this function lambda e is yet not very clear to us. We have not derived this because we have not dealt with the scattering in our analysis yet. And so this is if you recall the t equal to 0 Kelvin case, this was the conductance of a diffusive conductor at 0 Kelvin, and it was given by 2q square by h m2d EF times lambda EF W by L. But now in this case, the only difference that we sort of see is this 2q square by h times W by L is there, these two terms are there, and instead of m2d EF we have average of m2d E in the Fermi window, and instead of mean free path at Fermi level energy, we have the average mean free path of electrons in the modes in the Fermi window. So, this is sort of a generalization of the t equal to 0 Kelvin case. Okay. And again this is this average of m2de for non-degenerate conductors is given by this value. This we have already seen, and this average of, or this double average sort of mean free path can be calculated from this expression, and here we need to put we might need to use the Fermi-Dirac integrals and the expression for the number of modes. And so roughly we will sort of we observe that as I pointed this to you, that we have not gone into the scattering theory. So this expression, the expression for lambda E, we have not explicitly derived yet, but generally this expression lambda E looks like this. This is dependent on the electron energy above the bottom of the conduction band, and there is an exponent r here in this equation. There is a constant lambda naught which is actually not constant per se, it is independent of energy, but it depends on the temperature, and this is this Kb is Boltzmann constant, TL is the lattice temperature. So this scattering essentially depends on the difference between the electron energy and the bottom of the conduction band. So if this is the roughly the band structure, and the electronic energy is this difference between the electron energy and the bottom of the conduction band, this will govern the mean free path of the electrons in the crystal or in the channel, and this exponent actually depends on the kind of scattering mechanism that is present in the crystal. So for example, so the scattering can happen because of for example because of the phonons, because of the lattice vibrations, scattering can happen, and the scattering can also happen because of the interaction with external let us say electromagnetic field or external or impurity atoms, ionic impurities which are present inside the crystal, or maybe surface atoms. So there are multiple kind of scattering mechanisms, and this R is dependent on them. Generally using this formula for lambda E, this average of lambda is given by this expression. This is a detailed calculation, we are not going into the details of this calculation, but this is how it would look like. And you can try to see where this comes from, and generally for the acoustic phonons, when we have phonons traveling like sound waves, this exponent R is 0, and in that case this average of lambda is equal to lambda naught. for r equal to 0 case, and in that case this entire calculation actually simplifies, and in that case we can write the conductance or the diffusive conductance to be 2q square by h lambda naught m2d, average of m2d in the Fermi window times w by L, or lambda naught by L g2d in ballistic case. And in ballistic case we have already done the calculation, so this calculation is actually becomes quite straightforward. And if we take this general expression for transmission coefficient, which is Te is equal to lambda E divided by lambda E plus L, in that case for r equal to 0 case, for just for the acoustic phonon scattering case, Te becomes equal to lambda naught divided by lambda naught plus L, and this the conductance will be essentially lambda naught divided by lambda naught plus L into G ballistic conductance, or the resistance in diffusive case will be inverse of that, which is essentially 1 by L plus lambda naught into the ballistic resistance. And these calculations we have already done, the calculation of ballistic conductance and resistances at room temperature. So, these calculations can be done similarly. So, this essentially completes our discussion on the calculation of conductance and resistance for ballistic and diffusive conductors, both at low temperature limits where calculations are easier, and high temperature limit where calculations are a bit difficult. But with the help of Fermi-Dirac integrals, the calculations can be simplified, and especially for non-degenerate semiconductors these calculations can be easily done. So, with this the final idea will be the idea of mobility that we will start in our next class. So, thank you for your attention. See you in the next class where we will discuss this idea of mobility in ballistic and diffusive cases.